our productivity in our group, and a huge reason is that as we have just fantastic grad students that work with me who are motivated and have great ideas. And so 3 of them in particular have kind of contributed to the work that you'll see today. And then also, obviously our funders we really appreciate. So some of the work is funded by the National Science Foundation, and they're really on a push lately to show people that their work is relevant and that it's useful. And so they like for us to go out and talk about our work so that people can see that they're funding things that are that's useful information. And in particular, Branko Kirkes is a collaborator in Michigan that I work with. And so I'll show some slides from him. Joan Nassauer is another person on the project that works on social and kind of social barriers to using some of the stormwater practices. And then we have other partners in Virginia, MNet, which is a private company that is now owned by Xylem, who's on the project with us as well. And then some of ours is from the Institute of Secure and Sustainable Environment. So that's an institute here at UTK. And they do a slew of different things from clean fuels to water to waste management, just a huge different amount of things that they work on. And that's an institute that's funded by the state of Tennessee. And my collaborator through that is Dr. Kojandi from Systems Engineering. And she's my data guru. I always, whenever somebody asks me that they have a problem with data, or they want to learn about big data, or they want to process data, I always tell them to go to her. And she's like the only person I've met who likes data more than I do. So here's an example of what's right outside my door on a given rainstorm. So this is Second Creek. Second Creek is right next to my building. And Second Creek has huge urbanization issues, a highly impervious area. And so they say a picture gives you 1,000 words. And so I think a video is really impactful to show you, what urban hydrology looks like. And most of the people on the call are familiar with, the degradation that gets caused as a result of urban stormwater. And what we've done over the past, 40, 50, 60 years is we've really matured or changed how we looked at stormwater management, from something that's just flood mitigation to something that's flood mitigation and water quality to something that's flood mitigation and water quality and ecology and aesthetics. And so we're forcing a lot more out of the systems that we have. We're asking these stormwater systems to play a lot of different roles. And so as stormwater professionals, we may be interested in stormwater quality, but a lot of times the best way to pitch a project or to get people excited about a project is aesthetics or recreation or these other attributes that we talk about. And so as we kind of push these limits of what these practices can do, we need new strategies, and we need a new understanding and a better understanding of how they function. And so this is my research group. We work in this area of sustainable urban water. And so on the right, I just have a few of the things that we've been working on, maybe our bigger initiatives so far. And so we've done a lot with tree contributions to stormwater management, working with the Forest Service. A lot of communities across the country are trying to figure out how they can get credit for tree plantings and what role trees actually play in stormwater management. We do a lot with green infrastructure, how we can modify them to get the most out of them, right? We're pushing more out of our practices because we have all these needs. And then also how to model them. So can we model them well at the site scale? And that helps us figure out at the watershed scale what they're actually doing. Watershed scale runoff and water quality dynamics. We don't know a lot about how to model water quality in urban areas. And so there's still a lot of work to be done there. And then smart stormwater is what we're going to talk about today. So this all comes back to Internet of Things. And so it's the idea that we're becoming more and more connected. Our objects are becoming more and more connected. So we have this interconnection between commuting systems and it's allowing various things to be connected to the internet and to communicate with one another and to essentially start building these things. Sometimes we call them cyber physical systems, which means there's this computer element to it and then there's this physical element to it. So over on the right there, that's an example of one of my students, Aaron, and this is a very complicated solution to an easy problem, which is essentially he wanted something that would just like start his coffee maker in the morning. And so he built this contraption. So it basically like fills up the Keurig and like does everything for him in the morning. And so Aaron does a lot of work with us on our smart cities research and does a lot of like development of the sensors and stuff that we're using. And so this has been applied in a number of different ways. For wastewater systems, the idea of controls and the idea of computer systems is a little bit more developed. So there's cities that have a lot of sensors, and there's cities that have areas that they control. They can turn things on and off. This is an example of the system around Detroit where my colleague Bronco works, and they have up to 100 plus sensors around their system, and they've got 20 control points, which basically means these points where they can, as you can see on the right, they can fill up these inflatable bladders to like keep water stored in certain areas in their sewer. They can change the flow regimes in their system. And what he learned is that they were never actually using any of this equipment. They had all these controls that were installed and never utilized. They've got huge issues with combined sewer overflows into, and so they essentially asked him, or they were like, what can we do with this? And he did some simple optimization routines of like, if you actually used all these control points, what could you get? And essentially what they found out is they could save the city $500 million in infrastructure costs if they implemented and started using these control points in like a coordinated effort, right? So just by using the infrastructure that they had in a different way or actually utilizing it, they'd be able to save that much money in costs from things like combined sewer overflows. This is another picture of him down in Mexico City. They had a project down there where they were looking to look at the quality of drinking water and kind of apply it in a public health environment. And so they built these simple sensors to go down there and basically, measure potable water and see what kind of pollutants were in there. And so this idea of smart cities and smart water is really a developing area. And there's a lot of places for research, but a lot of possibilities. So when we talk about smart stormwater, we're taking those ideas and we're just applying them in this urban context, right? So we can put things like rain gauges and soil moisture sensors and things around our watersheds and better understand what's happening in them and how they're functioning. But we can also start adding in these control points where when we get that information, we make decisions. And so that's the next level, is not just getting information in, but making decisions on that information, and then actually changing the way that things focus based on the data that we have and the decisions that we're making. Okay, and so what we see is that a lot of previous work that's been done on these is focused on these open water systems. And this is some of the work in Michigan. One of the sites that we work with is a watershed in Ann Arbor, where they have these storage units they put in to basically control water coming out of their ponds. So they're focusing on site scale optimization, and they're really looking at hydrology and hydraulics. And we'll talk about how we're kind of building on some of that work here. But the city is excited about the possibilities that they can of reduced flooding and reduced infrastructure expenditures by utilizing the things they have. So this is our big project with Michigan, Virginia, MNet, and our group here. So two things that we have. One thing I noticed actually is that on the proposal, apparently Bronco spelled my last name wrong. So if I was NSF, I would have thrown it out right there. Hathaway's name is not spelled right. So basically what our goal or our pitch on this is that we know a lot about the technologies. We have sensors, we have controls, we have ways to push data around. So what's missing? Well, we don't know exactly what happens when you start applying this to things like green infrastructure. And then we also don't know a lot about if we start putting multiple things in a row, if we put 5 ponds in a row and have them act together, how does that work and what's the best way to do that? And so our project was intended to deal with some of those unknowns. So the first thing that we did is basically looking at GI, like can we go into things like bioretention cells and start changing the way that they function and basically make them function in a more optimal way. So this is our cross section of a bioretention area. Bioretention obviously has a lot of things going on, but in general, we've got this soil media in here, right? And that soil media has some wet spots, some dry spots. We get a lot of different pollutant removal that's going on in this system through absorbing nutrients, through converting nutrients, through microbes. And we can change the design. So we could let the water just perk all the way through. We could let the water go out through a drain. We could add this submerged zone. We call this internal water storage. And it's just the idea that we add a ponding zone inside of that bioretention. And what we did in our project is we basically mimicked those two things. So one is free draining. We let water basically perk through the entire column and out of the bottom. The other one is internal water storage, where we essentially force water to pond inside of the system. And what we did on these, a lot of column studies just, they don't have a way to basically mimic infiltration. So what we did is we put another valve on our system that we can let water slowly seep out of the bottom at the same rate that like a clay would seep out of the bottom. So we're trying to get at that idea that like, you know, water is not just standing inside of this thing, but there's actually some seepage going on also. And then we have these other two things over here. And what these are we essentially add a valve to that pipe, and we can tell that valve when to open and close based on what's going on in the system. So this one, we've got these soil moisture sensors that are in our column, and we can basically say, when you hit this optimal soil moisture, when you hit the soil moisture that we think is the best for microbes to function, we want you to stay at that level. So if it goes above that level, start draining some water out, right? Volume control basically means we want you to stay at a certain water level, and I want you to let water out or close your valve based on what's going on with that water level. So here's some of our designs here, our columns in the field. You can see we just have these little solenoids that we can open and close. So this was quite an effort to get this stuff together. We've got this greenhouse that we basically put all these columns in. And so this is like our little playground now, this greenhouse over off of Alcoa. And we've got columns that we can measure evapotranspiration. We can do stuff with these smart controls. We can do all sorts of different work. You can see this mixer in the back. So we fill it up with water. We put in artificial stormwater. We add some sediment to it, and we can use that and basically distribute it. And then Aaron's actually working on like an automated way to distribute it, to make it, you know, distributed more along the lines of what it would get during a storm event. So this is what we do, and this is essentially how these stormwater controls work. You've got some rainfall prediction that happens, right? So when you pull up your phone and it tells you it's going to rain 0.2 inches tomorrow, or what's the % chance of rain? Those are all these predictions that places like NOAA send out that tell you what's going to happen. And essentially what we can do is we can tell our column, hey, tomorrow, or it's going to rain about 1/4 of an inch. So I want you to prepare yourself. So what the column does is that it reads its sensor readings. It says, okay, my soil moisture is at 0.3. And if I get 1/4 inch of rain, how is it going to change my soil moisture? And if it's going to be a problem, I'm going to release a little bit of water. Then we basically simulate that rainfall event, and we let this column basically return to its normal operation. So post application, it's going to read all of its sensors again, and it's going to act respondingly. And so what we find is basically with our soil moisture dynamics is what you would expect, essentially, that this is a soil moisture sensor that's higher up in the column. This is one that's lower in the column. And you can see upper in the column, this internal water storage, when we have that constant pool of water, we're basically promoting higher soil moisture. We have these free draining systems that just drain right out of the bottom. We have these drier conditions. And then in the middle, we have our two control systems that are kind of acting right in the middle of those two extremes, right? And why does this matter? Soil moisture matters for a lot of things. For plant growth, for microbial action, which goes into pollutant removal. We really care about what's going on with soil moisture in our system. And in particular for water quality, we can start looking at things like nitrogen and nitrate removal. And what happens is nitrate removal is is going to happen under our wettest conditions, right? We start getting denitrification that happens over here. And so you can look over here and you can basically see that IWS that had the wettest conditions is also producing our lowest concentrations of nitrate, like we would expect. Our systems that are free draining are producing the highest levels of nitrate, which is what we would think. It's free draining. It doesn't really have a lot of moisture in the system. And so it doesn't promote that conversion to nitrogen gas. And then in the middle, we're in the middle with our two controls. And this was kind of our theme, is that we're able to kind of balance the difference between these internal water storage systems and these free draining systems with these controls that we have. We're like we're basically pulling the best from each of those units and able to put them in our systems. We also do stuff with microbial analysis. These are, these microbes over here are basically microbes that would be responsible for nitrification. And you can see basically how they differ depending on the system. So nitrification is generally lower in these IWS systems. We can see it from our soil moisture, we can see it from our water quality, and we can see it from the microbial community. Free draining systems tend to have higher abundance and higher numbers of nitrifying bacteria. So we see that. And then over here, we actually see that our control systems are functioning really well, and they seem to be a spot where these nitrifiers like. So we're trying to look at these like multiple lines of evidence of like basically showing what we see in the data. Does it make sense with what's happening in microbial community? We look at it from a hydrology perspective. So, you know, how does free drain versus these internal water systems differ in terms of where the water goes? So free draining, yes, I don't get much overflow in a free draining system, but I get a lot that's just leaving through an underdrain. So we're learning a lot about, not just about controls, but about how bioretention areas work and ways to get them to work better from a hydrology standpoint, from a pollutant removal standpoint. We have some kind of cool work that's kind of ongoing in this area, as you can see. Other stuff that we're working on is moving out and doing a little bit of more site level work with ponds, and this is in partnership with Knox County Stormwater. And essentially, we're focusing in on this on Connor Creek. So Connor Creek is over in Hardin Valley. If you're familiar with that area in Knoxville, it's actively developing. There's a lot of stuff that's going on in that watershed. There's like a new development I don't know, it seems like every 6 months there's a new development that's come up in Hardin Valley. And so it's a pretty fast urbanizing system over there. So we had a few things that we're trying to gauge. And so here's our study site. This is about, I think, 6 to 7 square miles of this watershed over here. Our site is here, which is about 1.5 to 2 square miles of watershed by the time we get to there. And this is the site that we kind of worked with. So this is Hardin Valley, and there's basically a high school, there's an elementary school, there's a middle school, all here in the same area. And what they have as part of their stormwater system is these ponds over here. And so we took this as an opportunity to work with the county, and NSF, National Science Foundation, actually gave us some additional money to work with specific partners on implementing these things. And so we're basically taking control of these ponds and essentially trying to look at how we can make them work together to provide some benefit in Connor Creek.
So the first thing was to create these low-cost gauging stations. So this is another one of Aaron's creations over here. And for about $200, he was able to figure out how to put together a board that can relay data basically relay data. We store that data at Amazon Web Service, and then we push it over to our visualization screens. This is what one of them looks like in the field, and because we're using ultrasonic, we have to like have it above, pulling or sending signals down against the water profile. And then we have to build our stage discharge relationships. So we go out there and we basically collect that kind of data. And we put these on 3 different locations on the stream, where we can look at what's going on. Okay, so we're investigating the impact of what happens with water quality inside of this pond. Not a lot of people have looked at water quality as part of real-time control. We're looking at what happens basically with turbidity, and that's kind of what we're focused in for this site level. So here's our pond over here, and we had we worked with the city. We had to do some modifications to kind of get it to work the way we wanted it to, but I don't know who took this picture, but this makes the pond look really good. I feel like it normally, when I go there, it's not necessarily looking like this, but this is like this is your selling point when you send out a brochure on your project. So it's pretty easy. We just install this valve over here. That valve has a metal stem that goes up over here. And then this thing can just turn this gate, just a typical gate valve. And so what we can do is we can remotely essentially tell that gate valve when to open and close based on an objective that we have. So we can either do it manually, or we can give it code and say, hey, if it rains this much, I want you to close. Or if your turbidity reading hits this number, I want you to open again. And so this is the type of stuff that we're working with. We get a big kind of range of water levels that are possible in this system. I'll talk a little bit about why that matters. But you can see it gets super full. And if you look at the difference between this and this, there's a lot of water that gets stored inside of the system, like a huge amount of water. And so you would think, like, does this pond make a difference in the grand scheme of things? This is the water level inside of Connor Creek. So we've got one that's really way upstream in Pellissippi, one that's upstream of our site, and one that's downstream of our site. And you can basically see that these are just depths, right? So these are like this is 2 or 3 centimeters. So this is only like an inch or 2 that things are going up or down, but you can see that these ponds do impact the hydrograph. And so you do see like an impact of what you're doing from a control standpoint inside of the stream, which gives you an opportunity to do some interesting things and to try to figure out like what is your objective for a stream like that. So I'm just going to show you. So essentially we've got dashboards that we make for all these things. We can pull up these dashboards and figure out what's going on inside of the creek. So this is real-time data, and this is from that pond. So this is happening basically now. You can see up here in green that we've got some rain that just happened. Right now our valve is like, it was mostly open coming up, and it shut for a little while, opened up, and now it's shut again. So it's kind of like, it's preparing for this rainfall, waiting for more rain to come in. But it didn't really rain enough out there you can see the water depth is still, pretty minor. So the rainfall has not really done anything for it out there yet. So we can look at stuff like that. We can look inside the creek itself. So this is what's going on in Connor Creek. You can see the upstream and downstream levels and what's going on. There's been a rise of a couple inches in the stream, but not a whole lot. And this also lets us essentially look back in time, so we can look at the last 90 days and see what's been going on with our pond. here's water level over time. So you can see these different events that came in and how much the water level rises. You can see how turbidity changes inside of that stream. You can look at rainfall amounts. And then this dashboard's cool because you can basically, I can take a figure like this and essentially download the data that's associated with that figure. So you can just get the data whenever you want it. So we basically push this to Amazon. We take it from Amazon and we put it on this. This is Grafana. And it's pretty nice. You can take all these data, you can do different types of dashboards, all different kinds of things like that. So inside of our turbidity, we've got these turbidity meters, and this is how we're getting this data as these Campbell Scientific. Turbidity can be more of a challenge than people realize. You have to, a lot of the sensors are optical sensors, which means they cloud over very easily. All of these sensors can be problematic depending on how they're designed, how they're made. So this one in particular, you can see over here, this is a bunch of stuff growing on it, and it's got a bunch of algae. But this one was made so that it has this rollback. So this piece basically moves off when it's ready to take a reading. You can see you can see these optical points right here, and so it's basically keeping it clean. So we tried to pick one that was a fairly nice quality. All right, so right after a storm event, this is what our turbidity looks like. And so what we tried to do is say, you know, if we basically held water back, can we get turbidity to drop down to some level that's acceptable before we discharge? So essentially when our pond, or when our gauges show us that rainfall is happening, we close that gauge, and then we're going to give it a maximum of 17 hours. So at 17 hours, we pull the plug on it and water leaves regardless of what the turbidity is. But what our goal is basically to hit 25 FNU before we let the water go, right? So we've reached some like basically cleaner water before we let the water go. And so here's our example over here of a pond hydrograph. You can see the pond filled up for some event. Our turbidity went up, and then our turbidity is going to drop over time. And fairly small particles, it takes a long time for things to drop. But you can see it keeps on moving, and then it hits below 25 at some point, and then we're like, okay, we can start discharging now. So we're trying to basically relate pond function to water quality to some degree, where turbidity is one of the easier things that we can like first kind of tackle before we start tackling more challenging things. So 60% of the events that we measure, we're able to meet that 25 FNU turbidity threshold, right? And it's just simply by holding water back and not allowing it to release right away. So the idea is that these ponds work through gravity. They fill up, you size the hole a certain size, so they're going to drain based on gravity and whatever size hole that you made, right? And so now we're kind of looking at that as an opportunity to adapt that system and let it function in the way that we want. So our next kind of battle is to understand how, this is our pond that we've been looking at the whole time. What happens when we start controlling multiple ponds? And we're just starting to look at this right now. We saw the impact of one pond in a stream. How do you basically sequence these ponds together to come up with some outcome? And there's been studies that have, and modeling efforts that have shown that in watersheds, if you just put in ponds like this in your random locations, you can actually end up with higher flows inside of your stream than you would have without any controls. And the idea is that these ponds can actually, discharge can coincide with each other, and they can cause more of a problem. And so what we're trying to think about is, can we control these ponds in a way that lets the ponds act together to reach some outcome in that stream? So these are the other ponds that we're monitoring over there. You can see our boxes and our stuff over there. So what types of things can we control, and how do we manage connected stormwater ponds in a watershed? right? And it brings us back to like, what is the objective of an urban stream? And what types of things are we controlling for? Are we supposed to control for flow? Are we supposed to control for erosion in the stream, for ecology? And we may choose to manage things differently depending on what that objective is. So there's a lot of work to be done to figure out what an urban stream is supposed to look like in terms of flows. When we just talk about infiltration and removing water out of the system, we sort of assume that the stream is going to have some benefit, but we don't ever really follow up to make sure that the stream actually gets the benefit that you think it's going to get. The other thing in this project, and we work with City of Knoxville, Chris Howley on this, is social barriers. So I don't know if anyone on here has gotten one of these flyers, but we had these flyers that went out in town about people's perceptions of stormwater controls. And we had a bunch of different ones. We had some where we were like, you know, what if we stored water in this parking lot? What would you think? Or what if you, and what these are supposed to show is that there is huge like ranges that you could see with things like ponds in urban settings. If you started controlling them, you know, you could draw down the water a bunch before a rain event that's coming in. And maybe you end up with some muddy side slopes and like a place that looks like it's been dried out. You could hold water back and have a bunch of water in that system. And so maybe it looks like it's like overfilled like this. Versus this is what it would look like during normal conditions. And so the idea with this study is like, what do people think about this? Like, you know, does something about these different strategies or different situations strike you as being like, from your perception, is there something wrong or is there something bad about what that system looks like? And it helps us put not just engineering, basically like, what am I trying to think of? Basically our maximum and minimums of what we're allowed to do, right? We're trying to put our controls on like, what's the most I could pond water and still have people appreciate that resource? What's the least water I can have in the system and still have people appreciate it? So there's some balance there about what people think about the system and actually trying to manage based on what people think and what their perception is of the system. So these are actually renderings that were done. Basically the group at Michigan like take a picture. And so I think this one is the actual picture. And then these other ones are just ones that they basically rendered. Same thing over here. There's just differences in rendering. So we sent out that flyer and they're going to be working up that information also about people's, what they think about how much or how little we control. The last thing that I wanted to talk about today is another little project that we've started on, and we don't have a lot of information on this, but it's another application of using science and or using sensors and data, and that's GI maintenance. And you know what we know and what I know from working with lots of different municipalities is that maintenance is a huge burden. We work a little bit with City of Nashville, and I know, you know, for their program, they have multiple staff who's like, are dedicated to inspection and maintenance, right? Like it's a huge burden. And in that, each one of these sites maybe gets inspected once a year or once every couple years. So what if we had a sensor array that was cheap and that people would implement with these different practices that could tell that there's some issues that are happening before they actually happen, or that could notify people when there was something that needed to be looked at. So here's an example on the left. You can see this is a bioretention area that had a bunch of fines that got into it. You can see it's got this big clogging layer on top, right? And over here, this was a site in Raleigh that I worked on. All these things back here are actually salt, for salt trucks, these big salt bins that were flowing into this bioretention and like killing off all the vegetation. So all the other trees in the system had leaves. You can see this tree is not feeling so good, right? So what we thought about is that you should be able to tell from sensors some of these maintenance needs. For instance, we have light sensors, right, that we could put under a tree like this and basically tell if that tree has leafed out or not based on how much light penetration you've got from your sensor. Over here, if you have a soil moisture sensor or you have a depth sensor in this system, you should be able to tell, like, if it's clogging, you'd be able to see different signatures in that sensor data. And so that's what we're trying to get at in some of this. And so this is like, we just got this project going, but essentially we have these columns where we put all this different stuff in it. So we've got these little pools up top, or these ponding areas on top where we let water pond. And then within that, we've got a float switch, we've got an ultrasonic sensor, we've got soil moisture sensors in there, we've got pressure transducers, and essentially we're trying to monitor a bunch of different data streams in here and figure out which ones of those data streams are important and which ones might be able to show us that maintenance is needed. So these are sacrificial lambs, most of them. We're gonna like be doing things to them on purpose to try to get them to not work anymore. So like dumping a bunch of dirt in them and clay and like trying to get them to clog, and then basically seeing what the sensors do as a result of that clogging. And what it does is it helps us take a data stream from a normal system, take a data stream from one that's clogged, and we can kind of compare those two things. Or we can look at how something has clogged over time and basically start assigning these patterns to it, right? So here's a data stream from soil moisture from a column system, and this is typically what you want to see. You get a rise in soil moisture, and then it basically, you know, as things seep through the system, you kind of get this slow drawdown. Next event happens, slow drawdown, etc. So what we contend is that your soil moisture should change, or these water contents should change if the thing is clogged. So it's probably going to go from something like that to something that more slowly increases in water and then slowly declines over time. All right. And this is why I work with systems engineering, is that they're really good at looking for patterns and looking at predictions based on data. Okay. So they're experts at basically taking data streams, looking at how the data is shaped, changes in the data, anomalies in the data, deviations from expected function. That's what they're really good at. And so we work with them to help them, or help us, identify patterns and identify anomalies inside of data streams like this. One thing that you realize when you start monitoring is that it's easy to collect a ton of data, and it's harder to make sense of that data and to know what to do with it. And so, you know, when you start working with data streams like this, it's a lot easier to have something that you're looking for to begin with than to just kind of search for things in the data afterward. You know, having like you know, your hypothesis or your theory on what things are going to look like is really important. So this is an example of the types of things that they do. This is one of our soil moisture sensors here, is in blue, right? And basically they're taking data like this. This is soil moisture sensors at 2 different depths, right? I believe the yellow is about 1 foot deep in a column and the green is 2 feet deep inside of a column, okay? So what they can do is stuff like this. They use these machine learning techniques, and they essentially, what they did is they took this, this blue line. This is the soil moisture, I think at 2 feet deep. And they took a data stream from the 30, I'm sorry, yeah. They took a data stream from the 30, or the 1 foot deep, and they basically tried to predict what's happening 2 feet down inside the soil media based on what's happening 1 foot down, essentially. So they're basically comparing, and you can see like they're able to predict this extremely well based on just big data streams. So they're basically taking one thing. I know my soil moisture 1 foot deep, and they're basically predicting, like, I can tell you what's going on at other depths inside of this thing just based on that one data stream. And so we're working on ways to not only do that, but to incorporate like rainfall, where we would say, based on the amount of rainfall, this is what we think will happen with soil moisture. Did that actually happen? So we're trying to do some like prediction and stuff like that inside of our data streams also. And the whole goal, and we have some proposals that we put on this, or we put out on this idea, is to basically inform municipalities, make their job easier and make their job more effective by, you know, you've got a dashboard and your dashboard sends you a note when, you know, fire retention area A is acting weird. It's, you know, its soil moisture readings have changed over the past year and now it looks like it's getting clogged, right? And we basically say, well, what if we could just send a note to somebody that says, hey, you should go look at this one because, you know, there's no leaves on the tree and the tree might be dead, or there's clogging in the system, we think, so we can go look at it. So that's kind of where we're trying to go, is basically giving people data and information to be able to go through. We've been working with data for like this for a long time in different aspects. We've learned a lot about what people kind of like and don't like. I had grand visions of just giving people data like 5 years ago. And then I realized that people don't really want just big random data sets. They want data that's like curated into something useful. So that's what we've tried to do recently, is like try to take data and make something useful out of it. All right, so that's kind of a snapshot. I just wanted to talk about like one of our research thrusts. You can tell a lot of the stuff is ongoing. We've got 2 PhD students that are working on these projects right now that are kind of midway through their program. And so there's a lot of work that's left to be done. You can contact me anytime. I'm happy to chat about any of this stuff or the other work that we're doing. And we try to keep our website, you know, semi up to date with some of the projects and the students that are working on things. So I guess we have a few minutes. If anyone has any questions, I'm happy to chat about it.
Anyone have any questions? This was great. I had a couple of really good chats saying great job and good information, and people are really enjoying it today.
One person's asking who we're working with on the data. So some of the new sensors that are coming out, we do a lot with this with these particle boards. They're let me see if I can find one. Particle is basically, these right here are these particle boards, and they have these ones called borons, and borons are essentially they're ready to go with like internet connection. So essentially boron has their own relationships with cell phone carriers, and so you can transport data through boron system, and they're taking care of all that stuff with cell phone carriers behind the scenes. So hopefully that makes sense. But yeah, you can get a boron basically chip, and you can basically pay them a fee based on how much data you're transferring.
I believe Walter Graff had a comment or a question.
Yeah, thank you. Hey, John, it's a good presentation you got going here. I just want to make a comment. It's like really this sort of work you're doing really helps to marry up or bridge the gap between green infrastructure and the built infrastructure. I think it's a huge improvement on helping our reduce the size of the types of conveyance systems we need when you can use green infrastructure to help mitigate the overland flow to our storm sewers, and also helps to prevent combined sewer overflows as well.
Yeah, I mean, people who know me know I'm a green infrastructure guy. I love natural systems, and I love the idea of like implementing these natural systems to take care of stormwater issues. The reality of the situation is that that's probably not always going to be the right solution for a given situation, and that these things there are other opportunities to do innovative things that can build on green infrastructure, like you're saying, that like, you know, incorporate green infrastructure with ponds, or allow ponds to do some things with like with mitigating stream hydrology issues. So I think the more tools that we have, the better in terms of stormwater management.
Yeah, I mean, I was saying that from the perspective is we're starting to look at like the digital sewer shed is what we're calling it, or digital, you know, so if you have not only your green infrastructure, your stormwater flow, and all of your infrastructure within a sewer shed or a drainage basin area, it's all linked. So the IWS component helps to make that linkage a lot easier and help everything work in concert.
Yeah. AWS service, I can't remember how much that is. It's actually not very much for the AWS. I can't remember exactly what it was, but we don't pay a lot for that. The dashboard is essentially through this. Grafana is just like it's basically a product made by a company, and so you can basically pull in data from Amazon Web Services to Grafana. And the Grafana is like a way to like create all these dashboards and stuff like that. You can do that through that program. Karina, we talked about doing that. Aaron was interested in trying to use like an optical, basically with cameras, like doing the turbidity with cameras instead of having to basically like turbidity can be a pain, these optical sensors that are actually in the water. So he talked about trying to do this with a camera. I don't know. I think he got pulled over onto other things, but yeah, he was interested in that for a little while. Yeah, so for machine learning, for data analysis, somebody's asking about that. I work with Dr. Kojandi in systems engineering a lot, and she does stuff with the healthcare industry. She does stuff with my group now. I hooked her up with one of my neighbors who does stuff with like nuclear sensors. Essentially, you know, what I do is I provide like domain knowledge, right? So you got to know what questions to ask based on like the domain that you're in. But then she is really good at figuring out basically how to utilize big data, how to do machine learning to make sense of it. So she does a lot of like predictive modeling and stuff. And that's, yeah, she's fantastic at it. That's the person who I usually work with. I think, yeah, we'll definitely be publishing stuff out of that. This is Aaron's, this is actually his first paper, is like dealing with turbidity stuff. He's working on it right now. So, you know, we're like, I cannot say enough how much we've appreciated working with Knox County on the project. They've been excellent collaborators and have allowed us to do some, I think, interesting things out there. So yeah, are there any other questions?
Hey, Dr. Hathaway.
Yeah.
This is Ellen. Hey, I have a question about trees specifically.
Yeah.
So we're actually kind of in the process of redoing our BMP manual, and we're looking specifically at reforestation as a BMP. I didn't know if you knew of any good papers or anything to show its validity. We have a very large issue, just talking with our engineers and Jeff, about giving people forest credit when there's no way for us to enforce that forest actually happens in 30 years.
Yeah. One of the biggest initiatives that I've seen was by basically up in Chesapeake Bay. So there's a couple like initiatives up there. The Center for Watershed Protection up there built like a little model to basically try to say, like, if you implement a tree, this is the stormwater benefit that you can expect from it. So they've done like a fair amount of crediting, trying to relate trees to like stormwater benefits. So that's the place that I would probably look first, because
Okay.
they've kind of, they're like desperate for credits in the Chesapeake Bay because of their TMDL. And so they look at like everything under the sun as like, how do we credit that system?
Yeah, I looked at some of their papers up there, but a lot of them are specifically focusing on TMDL, whereas we have designers wanting to use it for peak flow mitigation.
Oh, okay. Yeah.
And like, so like, you know, using the area as forest curve number and using that for peak flow mitigation as far as their post-construction calcs, like saying that area is now forest, even though it's not really forest now.
Yeah.
So I haven't really seen anything as far as like peak flow water quality credits, if that makes sense.
I'd be interested to talk about that with you, because so a lot of times it depends on what it falls onto after it comes out of the tree. So like, is it impervious area it falls on, or is it like grass or something? Because there definitely is, there's definitely like a change in rate. So it does like slow the water down to some degree.
Yeah.
But I don't know that anyone's ever like equated that to a peak flow reduction. They're actually kind of trying to do that, but it's like maybe like a year off from that.
Yeah. Well, it might be good just to set up a talk to talk about this, because I think a couple other people have questions as well. But yeah, we've had a couple of ambitious designers ask specifically about reforestation recently. And we're just trying to figure out how best to apply that on our sites.
So yeah, email me, because there's a guy up at Syracuse, I think. Anyway, he like built the iTree Hydro. He built like the hydro part of iTree Hydro. Mm-hmm. And he essentially built that program so that it would take the canopy into account when it does its hydrologic modeling. Okay. So that's like the one tool that I've heard of, like a model that actually takes like canopy into account when it looks at like what's going on in the watershed, as opposed to just like applying a land use. Perfect. And I know he's wrote some papers on it, but we could look into some of that stuff.
Yeah, that sounds great. I'll email you.
Yeah, cool. Thermal impacts, we're interested in that. I think we do have a pond right now that we have implemented with no, we don't. We're looking at dissolved oxygen. Thermal is something we've talked about also, about like what are the thermal impacts of ponds on hydrology like this. We have a multi-parameter probe like in the stream right now. And so we're going to be able to, I think, see a little bit of like the pond impact in terms of temperature. So hopefully we'll get there.
John, I had a question that kind of goes back to your bio research, the bio cell research that you're doing. Yeah. I had seen a good webinar on what the Department of Defense was doing on inoculating the living material first to see if the improvements were made through inoculation. Are you guys doing anything like that? Or have you seen anything about that, and to treat for like metals and other things?
We have not done anything like that, but there is a ton of research. One of my friends is actually doing I think he's got a paper in review that's basically like all the different amendments that people have added into bioretention areas to try to, target metals or target all sorts of different things. And so, yeah, there's a lot of different things that people are trying to implement. I tend to think that a lot of those media amendments are probably going to be implemented on a site basis based on what the issue is. So like sometimes the Department of Defense or like scrap yards, there's like a hot spot of something specific. Like
Right.
this specific metal is a hot spot. And I think those have a really nice utility, those amendments in areas like that, where there's like a specific thing you're worried about.
And this was kind of that, I think it was cadmium they were doing, and it wasn't the soil amendment themselves, but they were inoculating the root with this like rhizome that had a cumulative synergistic effect on removing, which was pretty interesting.
Yeah, there's all this like stuff people are doing with like fungi, stuff like that right now. That's kind of cool.
Well, thanks. You guys are doing cool work up there.
Yeah, thank you.
Anything else?
Hey, John, this is Josh in Chattanooga. How does this compare to any of the OptiRTC stuff that's out there?
It's basically, I don't want to say it's the same. It's very close to the same. So the guy that I work with at Michigan, like he's got grad students that go and work for Opti. He's, we're basically doing similar things to what they're doing. I would say the differences between the stuff that we do and what they do are, they've been doing like, they've got these really nice like packages, and their stuff is going to be like clean and they're not going out and like printing their own boards and like putting together 2x4s and stuff the way that we are, right? So their installations are going to be like, what you would expect from buying something from a company, right? What they're not going to be as good at is like exploring these interesting little like side notes that we are. So like they're not a research company, and so they're not, our job is to try to push these things in new directions. Like, well, what if we did it this way? Or how could we answer this question? And that's not what they do as a company, right? So I don't know if that makes sense or not. Like,
yeah, I'm wondering if anything that you guys are working on or developing that they would want to take on and implement.
Yeah, so the company that we work with is MNet. MNet basically does what Opti does. So if you know like Mayor Pete Buttigieg, he wrote a book about in South Bend, and in the book he talked about like wastewater, like a wastewater system they have in South Bend, and that company is the company we're working with, MNet, which is they're basically do the smart water stuff the same way. They've done more stuff in a sewer environment, but it's the same type of work. And so, yeah, we're working with them on this project, and they work a lot with, or they've worked a fair bit with my collaborators in Michigan. So, for instance, there was this effort to take Swim, the model Swim, and basically recode it inside of Python so that you could do some new things with it. And that was basically that MNet group and my collaborators putting that together, and now tons of people are using that program. So, we definitely are producing things that people like that are interested in. Yeah. So,
all right, just making see if anybody else had any comments for.
Yeah. But Josh, yeah, you can get this stuff where, if we wanted to like the screen that I showed these little stream sensors like this, like we're not a company, and so I'm not going to like bust out 10,000 of these. But if we had a project where somebody was like, we want to build 100 of these, that's basically what they're doing at Michigan and the stuff that we could do. We have a board design, we have the programming for it, we've got all the ability to like put it on Amazon Web and push it to dashboards. It's not that hard for us to get a bunch of undergrads and basically solder and put together boards like this. So, we have the ability to do that. We're just, there's limitations. I'm not going to be able to do like 10,000 of them. But, you know, if we were to put together a couple hundred or something, like it's not that challenging to do. And in fact, a lot of the stuff that we're doing and that Bronco does is all open source. So his stuff at Michigan, he's got a website. You can go pull everything that he does on there. His code, how he builds stuff, all the materials he uses. He basically is like open source with all of it.
All right, anybody else? This was great today. We had a lot of good discussion, a great presentation, and we had a lot of folks. So yes, I am recording this. It will be posted on the TNSA Talk webpage. So it'll probably take me until this afternoon to get that done. It takes a long time for it to convert once I do this. So yeah, I think we have one other question, I believe.
About board design, the stuff that we work with. So the boron, the particle boron is basically like an Arduino. And so it's like the programming language and stuff like that. It's basically, that's what we're using. It's just a different, you know, they basically are taking the same thing and making that. So that's pretty much what we use.
All right, awesome. Thank you all. I have your information. If you did not have your name displayed where I could see exactly who you are in your description, just send me an email and let me know you attended today, and I will get the PDHs out to everyone. John, is there anything that you would like to send anyone, or anything, links or your presentation or anything before I send out the PDHs? I can send that all out together.
No, I mean, just, you know, okay. Everyone feel free to email me if you have additional questions, just hathaway@utk.edu.
And I'll send your information, your contact information in the email to make it easy for everyone as well.
Yeah. I mean, we love being a resource for the state. That's what our mission as a university is. So, you know, we're happy to talk with people.
Awesome. Well, thank you so much for today. Don't forget, you guys, we have annual conference coming up October 21st and 22nd. I believe I have the agenda mostly complete with the speakers approved. So I will get that out to you this afternoon on the website, and also send that out in an email. And don't forget to register for that. Our next TNSA Talk is at the end of October. It will be about the smart yards with Andrea Ludwig. So we're excited about that. And I think that's all I have. You guys have a great afternoon, and thank you so much, John. I really appreciate it, and thank you for attending, and I'll see you next time.
Yeah, thanks for the opportunity.
Yeah, thank you. It's been great.
Okay, thanks, y'all.
Thank you.